today, and it is my hope that the topics we have been treating, the ideas behind them, are actually and adequately understood. Thank God. So today we are continuing our discussion on periodic table, because it's a very important topic and very wide. That is why we are taking our time to explain what are the necessary information that need to be gotten as far as periodic table is concerned and chemistry as a whole is concerned. Today our topic, our discussion is going to be on some properties of groups and periods in periodic table, because I remember the last time we treated the properties of some groups, the important groups like group 1, the alkali metals, group 2, the alkali earth metals, group 7, the halogens, group 0 or group 8 as the case may be. Those are the noble metals. We thought it worthwhile to treat them briefly so as to help us in the chemical combination, which is a topic we are going after this one by the grace of God. Although we are still going to lay emphasis, much more emphasis on those groups, but for now the little information we need to know is what we have learned as far as those groups are concerned. So today we want to know the relationship between the elements in a group and in a period, because those relationships actually guide us in determining some physical and chemical properties and the way the nature of bond each of them will form together when a compound is being formed. This is a periodic table that we are familiar with, and we are made to realize that, for example, now between lithium and sodium, apart from the chemical properties that we said they are similar last time, and physical properties that we said they are similar but actually so different. So between sodium and lithium, there's a particular another property. Between sodium and potassium, there is one. Calcium up to potassium up to krypton, lithium up till neon. So there are properties like that that we need to study, because the way compounds are formed, they actually depends on the properties that we need to learn today. Although there is a diagonal relationship such that lithium and magnesium are related, beryllium and aluminum are related, but for our level now we don't need them. All we need to do now is to understand the concept behind the trends of all those properties across the period and down the group. The properties that we are going to consider are ionization energy, atomic radius, electron affinity, and electronegativity. And atomic radius, we can extend it to ionic radius, and electronegativity also by extension can be extended to electropositivity. Another importance of learning this topic is in application in another wide and important branch of chemistry, that is electrochemistry, because when we get there we are going to consider what is called Born-Haber cycle, and from the knowledge of electron affinity and ionization energy, lattice energy, which is difficult to calculate, can be calculated with the knowledge of ionization energy and electron affinity. And that lattice energy is very, very useful in Born-Haber cycle. We are going to get there by the grace of God latest. So let's just start taking these properties one after the other. Let's start from the simplest. We know that in a particular atom there is a dense core called the nucleus, and electrons are presented themselves in shells. It depends on the number of electrons. That is, we know if an atom we have one shell or two cells or more than that, as the case may be. And during the formation of a compound, it is either electron is gained or lost or shared. So what guides maybe electron is going to be shared or lost again is this ionization energy, which is the energy required to remove the most loosely bound electron from the outermost shell of the gaseous atom. This is what we are trying to say. From the nucleus to the outer electron, it is established that the electrons are not of the same grip by the force, as in the same grip of the force of the electron, the nucleus rather. The nucleus is attracting the electrons, that is established, but the way and manner the electrons are being attracted are not the same. That is what we are saying here. There is a particular one that is loosely held, is loosely bound by this nucleus. So the ease to which this electron can be removed is what is called ionization energy. You want to remove something, definitely you can't remove what is closer because it has a firm grip. It is actually what is distant, that is loosely held, that can be removed. So by doing that, it is reasonable to know that something must have contributed to what is called a loosely held or loosely bound or tightly gripped, and this will now translate to how they can be removed. Because we talked about reactivity the other time. The reactivity of metals or non-metals, it depends on this ease of losing or gaining electron. So now we are considering losing electron, and we know that metals lose electron, but the way they lose electrons are not the same. Lithium and magnesium and calcium, sodium, rubidium, francium, radium, they don't lose electrons at the same rate. So the energy that is required to remove these electrons, the outermost shell, because that is the one that takes part in reaction. So that energy that is required is what is called ionization energy. So now down the group, what did we study down the group? So we were made to realize that down the group, each of the group, they have the same outermost electron. If it is group 1, let's consider group 1 now. They have the same outer electron, that is 1, 1. So now, but as we are descending from one period to another, the number of shells increases. That is number 1. Number 2, the distance between the nucleus and the outer shell increases. So lithium that has one shell, the distance between that shell and nucleus will be smaller than sodium that has 2, will be smaller than potassium that has 3, smaller than rubidium that has 4. That is what we are saying. So as distance is increasing and more shells are being added, so we expect that there's going to be shielding effect. It's just like somebody that want to preserve something that is heated. So in science, we insulate it. So let us assume that we have only one type of insulator. Now, you wrap something by one layer of insulator, then another person wraps the same thing at the same condition with 2 layers, another one with 3 layers. So if after some time, if we feel the temperature at the outsidemost of that insulator, we are going to see that the temperature there will not be the same. That is the similitude of what we are seeing here. The outermost electrons are farthest from the nucleus, near the bottom of a group. So we don't expect those electrons to be firmly gripped to the nucleus, like what are being, those ones that are closer to the nucleus. So as we are experiencing much shielding effect, more shells are being added, then there's a greater distance. So it becomes easy for that element down the group to lose electron more than the element up of the group. So like this now, this is for lithium, this is for sodium, this is for potassium. You can see from the lithium here to here, distance is small. From here to here is more than lithium, then from here to here in potassium is more than inside of sodium. So it is easier, it's easiest here for potassium to lose electron here, this electron, than sodium to lose this electron, than lithium to lose this electron. So that energy reduces now, because number one, distance increases. Number two, shielding effect. 1, 2, 3. The 3 shells are shielding this one. Here, 2 shells are shielding this. Then only 1 shell is shielding this. So because of the shielding effect that is increasing, the effect of attraction will not be terribly felt by the nucleus of potassium, unlike by that of that of lithium. So we have more than one hydrogen energy, because elements can form more than one positive ion. It depends on the number of electrons that are removed. If we are removing the first electron here now, it's called first ionization energy. If we are removing the second, it is what we call second ionization energy. But in general case, second ionization energy is always greater than the first ionization energy, because it is easier to remove. It is more difficult to remove the second electron, simply because that shell will be completely filled. Like now that we have one shell that is filled, if we remove this shell electron here, so we have 2 that is completely filled, it is stable enough. This element will not be willing to lose any of this electron. The same thing here. If we remove this one, it will not be able to lose any of the electron here. If we remove this one, it will not be able to lose any of the electron here. So it is easy. So for group 2 element, that we have 2 electrons in the outermost shell. So if we remove the first one, so it remains 1 in the outermost shell. It can be removed, fine, but it must more energy, because the positive ion is more than the negative ion now. So there's enough force of attraction for that electron to be higher than the first one. Like if we take calcium as an example now, the first time calcium was having 2 electrons, 20 electrons and 20 protons. So if we remove the first electron now, so calcium will be left with 19 electrons and 20 protons. So 20 protons or 19 electrons, the effect will terribly fade. The grip will be much than when 20 versus 20. Now 20 positive versus 19 electrons. So that is why second ionization energy is in general higher than the first ionization energy. Across the period, what do we expect? We know from the last time that non-metals that are here, they don't lose electrons. So if we want to force them to lose electrons, we have to supply much more energy. Much more energy means the electronization energy is increasing. Down the group, it is decreasing. So let's go to atomic radius. From mathematics, radius is distance between the circumference to the center. And this distance is not easy to measure here, because it is very difficult to locate the outer shell from the nucleus to locate the distance. So the easiest way is to get two atoms combined together and locate the two centers like we have here. So the distance between them is like a diameter, because this is one radius, this is another radius. So combined together we have two radius, so making diameter. So to now get the atomic radius, since it's the same atom, so we expect to get equal radius. If this is 1, this is 1 also. So we now had 1 plus 1 together divided by 2, making 1. So 1 at the atomic radius. That is just an example. So the atomic radius is just like that, and we know that the bond radius can change slightly depends on what atoms are involved. And down the group, we expect them to be atomic radius to be increasing because of the shielding effect that we have talked about, and the distance, the number of shells. We have seen it even from the last time, and we have seen it with the ionization energy also. So this atomic radius that is increasing can even be used to explain the ionization energy, because the smaller the distance, the firm grip of the electron on the atom. So all additional electrons go into the same principal energy level. No energy have been added to the inner shells, inner levels. So electron shielding does not play a role as we move across the period. So across the period in the atomic radius, the atomic radius reduces because of the grip, the hold of the electrons to the nucleus, which is governed by what is called increase in the effective nuclear charge. Because across a period, any period, so we don't have more than the same number of shells. Like in period 3 now, we have 3 shells. So and we keep adding electron and proton, electron and proton, electron and proton. So we are increasing nuclear charge, the charge on the nucleus. That's the positive charge. We are increasing it from sodium, that is 13, to argon, that is 18. So we are increasing like that. So we are increasing nuclear charge. So we are increasing the atomic force between the nucleus and the electrons. So in that case, we are shrinking the distance, because if you can hold something very tightly, the distance will not be the same as somebody that loses his own like that. That is what we are seeing. So down the group, atomic radius increases, across the period it reduces. So this is the just like a schematic diagram to show how it is. Down the group it increases, then across the period it decreases. So ionic radii is more or less like atomic radii. That is just the average distance between the nucleus of the outermost shell of an ion instead of atom. So when we have sodium ion now, so that radius is the ionic radii. If we have chlorine atom, that radii is the chlorine ion, that radii is the ionic radii. So qualitatively, they have the same trend. It increases down the group, reduces across the period. But one thing is that we know that in metal loses electrons. So when a metal loses electron, we expect the radius to be smaller than ordinary metal, neutral metal. However, chlorine, when it gains electron, the size increases. So it is the same like that for other non-metals. So for metals, it is the same. When they lose electron, the size reduces. When they gain non-metals gain electron, the size increases. Down the group and across the period, the same trend as we observe in atomic radius. So electronegativity now. It is the willingness, the ease at which electrons are added. How atom can attract electron. That is what's called electronegativity. Electronegativity is a measure of an ability of an atom in chemical compounds to attract electrons. The atom with the electronegativity value will pull electron more strongly than the other atom will, because any atom that can pull electron, it must have a high electronegativity. Well, that's what we are saying. How easy can element attract electron? That is electronegativity. If an element can attract an electron easily, that's a very high value. So one American scientist, Pauling, gave, because when he did it, it was found that fluorine has the largest electronegativity value, so just give it 4. Then other ones are calculated based on fluorine as the reference value. So the trend is that down the group, electronegativity decreases. That applies to all the groups, from group 1 lithium to francium, from group 2 like that. Electronegativity reduces simply because it is easier for those elements down the group, any group, to lose electrons than those elements above them in that same group. So that explains that. For metal and non-metal, yes. Across the period, we know that metals, they lose electrons. Non-metals, they gain electrons. So non-metals has electronegativity value more than metals. So it increases like that. That explains that. So we can use electron shielding to explain it, although it doesn't make more difference. We can use effective nuclear charge to explain it, and the same thing as we have explained in atomic radius, because as you increase the nuclear charge, you are expecting a more force from the nucleus to the electrons. So in that case, we are increasing electronegativity value. Electropositivity is almost opposite of electronegativity. Electropositivity is a property of metal. The ease of losing electron, the activity, the way, the manner, the ease, the eagerness that elements lose electrons. That is electropositivity, electropositive. So the electropositivity is an ability of chemical compounds to lose electrons. The opposite of electronegativity, as we have said. The atom with higher electronegativity value will lose electron more readily than the other atom will. Yes. The francium is the most electropositive element. So the last element in group 1 is the most electropositive. Like we have the first element in group 7, fluorine, as the most electronegative. So we are having the last element in group 1 as the most electropositive, because it loses electron. Number 1, the distance, atomic distance, radius, is the largest. That's number 1. Number 2, ionization energy is the lowest. So it is easiest for francium to lose electrons. So it's the same. So down the group increases, across the period reduces, decreases. So it's the same like as we have explained. So electron affinity, this one is a bit more technical. I will urge us to listen attentively to the explanation. The energy change when a neutral atom gain electron. Before there was energy of that electron, so that element, electrons are now added. There's going to be a change in energy. So that change in energy is what is called electron affinity, different from electronegativity. The electron affinity tends to decrease as you move down a group because of the increasing effect of electron shielding. Electron affinity tends to increase as you move across a period because of increasing nuclear charge. So let us now try to explain what is called electron affinity. If we move across the period, electron affinity increases. So let us try to look at it as it is the opposite of ionization energy. If we don't forget, ionization energy is the energy involved to remove electron. If you want to remove electron, you have to apply energy to remove electron. Yes. In electron affinity, when atom gain electron, what is the energy involved? That is what we are saying. The energy evolved, energy lost. That is what we are saying. So it is easier for non-metals to attract electron than metals. And this value is negative value. The first electron affinity is negative. So we can read a book that is saying different things from what we are saying here. We just need to get their concept correctly. Number one, if a book tells us that electron affinity increases down the group, it is because they are taking negative aspect of this one, negative values of this, minus 60, minus 46. So that means the book is considering minus 46 as being greater than minus 60. That same book can be saying electron affinity reduces across the period. Maybe the book is saying that minus 60 is more than minus 328. So I want us to look at it from the perspective of, let us assume neutral element has zero energy. So the distance between 0 and the value of electron, the electron affinity, is as in the energy when the electron is gained is the electron affinity. So now, across a period, let's take period 2 as an example, the period where lithium is up to fluorine. So this is lithium 60, this is fluorine minus 328. So 60 is closer to 0 than 328. So 328 is higher in that aspect than 60. So at least we are convinced now that electron affinity increases across the period. 60 if we take 0 as our reference point. So this is minus 60, 328. Then this is 60. So positive 60. 60 is closer to 0 than 328. So the same thing here. Sodium 53. The other one here is minus 349. So 53 is closer to 0 than 349. So across the period, it increases. So down the group, let us try to look at it from 60 to minus 46. So 60 is farther away from 0 than 46, whether we take negative or positive. So down the group it reduces. The same thing here, but we are going to see that, as in we see that this fluorine, if we are to take that the electron affinity reduces down the group, these values should have been higher than this. 328 is lower than 349. What is the explanation behind this fluorine? Although we don't need it, let's just try to understand it. Fluorine has a very small atomic radius, and the electron in fluorine is, as in it has perfect configuration such that it is difficult to add electron to fluorine, although fluorine is the most reactive non-metal, but this doesn't translate to its electron gaining ability. Even in electronegativity value, it shows It has a lower value than chlorine. So it is easier for chlorine to attract electron than fluorine, because this fluorine has a very small size. The size of chlorine is bigger a bit than the size of fluorine. So that is why this value is like that. Let us leave it as that, because there is some physics and chemistry that are above our scope here at this level. There is what is called second electron affinity. That is the energy involved when second electrons are added. So that one is always positive, because the energy is needed to add the second electron. So it makes all of them to be positive. Even the non-metals, all of them are positive. But we don't need it. What we just need is to understand the trend, and that is what we have understood. These are points to note. In summary, down any group, atomic radius, ionic radius, and electropositivity increase, while electronegativity, ionization energy, and electron affinity, all of them reduces down the group. So the opposite is happening across the period. Electron shielding effect, then atomic radius, they are important when you want to explain the traits in the properties above, as we have seen in the presentation earlier. First ionization energy is generally lower than second ionization energy. We have explained that because it's more difficult to remove the second electron because of increased nuclear charge. The second ionization energy is positive, and in absolute terms lower than the first. What I mean by absolute term is that if we remove either positive or negative from the first one, like here now we have minus 328. If maybe the second electron affinity is like 150 plus 150, because it's always positive. So if we consider the absolute value of this one, 328, so 328 is greater than 150. I'm just saying 150. I'm not sure of the second the value. So let us consider the ideas that we have learned to answer some questions. These are examples. Each of the following belongs to the P block. We know that this is the P block or the periodic table. This is S, this is P, this is D. So P, Q, and R. We just look for that where we see P, Q, and R, and we choose it. That is question 85, question 1, 1985. An element with atomic number 12 is likely to be what? So if we know what the atomic number 12, we just need to write the electronic configuration 2, 8, 2. So 2 is the last, is the valence electron. So is it a metal or non-metal? Our understanding of the position in the periodic table will help us to quickly understand what is written here. If it is a metal, it is electrovalent. We are getting to that. If it is a non-metal, it is covalent. Atomic number 12 is A, magnesium. So it is a metal. So it is electrovalent. That is number 1. Sorry, its number is here. It's group 2. Then the outermost electron is 2. So that's the valence electron of 2 plus 2, B. Let us check our answers and see. Yes. So another example is, which of the following group of physical properties increases from left to right of the periodic table? Increases from left to right of the periodic table. We have talked about that. Increases from left to right, that means it's across the period. So we are expecting to see electronegativity, ionization energy, and electron affinity. So ionization energy, electron affinity, then electronegativity, 1, 3, and 4. So we are not seeing 1, 3, and 4 here. I want to believe it is a typographical error. JAMB 1986, question 9. Which of the following physical properties decreases across the period? across, yes, the periodic table. Across the periodic table, what properties decreases? Ionization potential, does it decrease or increase? It increases. Electron affinity, does it increase or decrease? Electronegativity or atomic radius? Which one? Let's still go back to our point to note. Across the period, what decreases? Atomic radius, ionization, atomic radius, ionic radius, and electropositivity. So at least we can get the answer from here now. Decreases across the period is what is called atomic radius. So the energy change accompanying the addition of an electron to a gaseous atom is called dash. We need to be very careful here. Addition of an electron. It is not loss of an electron. If it is addition of an electron, it is called electron affinity. If it is loss of electron, it is called ionization energy. So they put all of the options there so as to make students confused. And it is energy change. Energy change tells us something. Addition of an electron tells us another thing. So those two combined together, it is called electron affinity. Let's take our answers and see. Yes. So these are exercises that we need to look at after reading the whole and check our answers. This is the end of today's class. I hope you enjoy it. So we'll meet the other time. Don't forget to like and share the video.